we're going to work on the one in the middle of the page. It's about finding the moment of inertia about a point 1/3 the length of the rod. If it was in the middle of the rod, that'd be pretty nice. It's just right there on our table. So the middle of the rod and the end of the rod are on the table. But if it's any other point than those, we're going to have to go ahead and use the integral. Okay? So when we go ahead and use that integral, it's going to be the integral from the left end of the rod. Now this is the position of the left end of the rod, where our axis of rotation is at x equals 0. So it's the integral from the left end of the rod to the right end of the rod of x squared times the density times the cross-sectional area. This is what that lambda term works out to be for a uniform rod. Okay? So let's go ahead and start out by choosing x equals 0 on our object. So here it is. I want my axis of rotation at 1/3 the length, so that's where x equals 0 is. I want my left bound to be the left end, the position of the left end, and so that's 1/3 the length back. So I'm left with negative L over 3, and that's because it's on the negative side of x equals 0. And then my right bound, XR, is going to be 2L over 3. So let's go ahead and set up that integral for ourselves. All right. So my moment of inertia is going to be the integral from negative L over 3 to 2L over 3 of x squared density times cross-sectional area dx. Now when we do this integral, I have this density and this cross-sectional area in my integral, but when I look over here, there is no density and cross-sectional area in this. So what we want to do is we want to eventually transform this into a format that looks like this, where there's a coefficient, a mass, and a length squared. Okay, and I'll show you how we're going to get that done in the end. All right, so let's go ahead. Since these are constants, I'm just going to move them out front and do my integral. So there we have. We've done our integral. We moved our constants out front. Okay. If you'd like to move your 3 out, we can move that 3 out now. Okay, since it's a constant as well. And then we can just plug this in. And so let's see what we get when we evaluate our integral. So we have top minus bottom. So I have 2L over 3 cubed. Now, because I'm cubing a negative, instead of subtracting, the negative is going to come through the cube, so I'm just going to make it a positive now. So I have L over 3 cubed here. All right. So let's continue to kind of simplify this down. We'll factor out anything that's in common. So here I have an L over 3 cubed. Here I have an L over 3 cubed. So let's factor one of those out. So now I have I is equal to density times cross-sectional area times length cubed, all divided by 3. And then I have another 3 cubed down there. All times, and I'm only left with 2 cubed plus 1. And for those of you doing the math in your head, 2 cubed plus 1 is 9. And 3 squared is 9. So I actually can cancel some of this stuff out. Cool. All right, so I'm left with this. I'm left with I is equal to 1/9 times the density cross-sectional area times length cubed. And I said, oh, we wanted it in the format of a coefficient times mass times length squared, but I have that density area and I have length cubed here. So how do we deal with that? Well, if you remember, density, our rho value here, is equal to mass divided by volume. Now, for a uniform rod, the volume is going to be the cross-sectional area times the length. Okay? Same idea for a cylinder, right? You do the cross-sectional area of the bottom times the height. Okay, so that's kind of what we got going on here. So I solve for mass. I found out the mass is equal to density times cross-sectional area times length. And so our trick, when we get to this bottom part and we want to simplify it into the format of coefficient, mass, length squared, we're going to want a friend. We're going to want to find pal. And so what I can do is I can look for pal in here, and so I can kind of break up that L cubed into an L times L squared, And look what we just found. We found a pal. And so that becomes our mass. And so our moment of inertia is going to be 1/9 ml squared. All right, try that next one on your own. Even though it is on the table, just go ahead and try it and see if you get the same thing, okay?